Welcome. We consider now a classical problem known as the two trains problem in physics. This is a 1D kinematics situation where we have two trains, let's call them train A and train B, and train A leaves its station and train B leaves its station. The stations are separated by a distance of 1200 kilometers, and they're headed towards one another on parallel tracks. We are told that train A is going at a constant velocity of 200 kilometers per hour. Here I'm providing some US customary units just in case you don't really have a feel for what a kilometer per hour is. So it's moving along pretty fast at over 120 miles per hour. Let me label this as the speed or the velocity of train A. And then train B travels at a constant velocity of 100 kilometers per hour. And we want to find the time when these two trains are going to pass each other on the tracks. We're also told to take the origin at the starting station of train A. To solve a problem like this, it would be helpful to draw a small schematic of what's going on here. So very simply, let's suppose this is where train A starts off. And clear out over here is where train B is beginning. And we know that at some point they're going to pass each other. We're not exactly sure where that is, but let's just draw, supposing that they cross paths at this point. Okay, if that's the case, then we could label this distance to be the position of train A, which I'll label as x sub A, and this we will label as x sub B. And of course, we were told in the problem statement that this entire distance is 1200 kilometers. Let's also put in here the fact that the velocity of A is given to us, and it's a constant of 200 kilometers per hour, and the velocity of B is half of that, which is 100 kilometers per hour. I'm going to try and solve this problem in two ways so that you get a taste of maybe a couple different approaches and not only looking at it by one approach alone. So let's look at first an algebraic approach, and then after the algebraic approach, let's look at this problem graphically. So in an algebraic approach, the first thing we notice after drawing our little schematic, particularly from here, we notice that the sum of XA, the position of train A, and the position of train B sums to the distance separating those two stations that they started off from. So this is an important equation for us as we go through the algebra here. The way to solve this algebraically is to do a rate type of a formulation, that is to say that, so the form, let me just say the form is that the distance is equal to the rate times the time. Okay, this V is what I'm referring to as the rate. Okay? Now let's go ahead and write the two rate equations. So for train A, we have x sub A is equal to v sub A times the time. For x sub B, we have the rate v sub B times the time. From this equation, we know that x sub B is equal to 1200 less x sub A. And so if I were to put this value in here, and the reason why I want to do that is to eliminate, see, as it stands, I have an x sub A, a v sub A, I have a time t, then I have an x sub B and a v sub B. So I have 1, 2, 3, 4, and I have 5 things that are going on here. But if I write x sub B in terms of x sub A, I've eliminated one of those 5. Okay, so I've got, therefore, 1200 minus x sub A is equal to v sub B times t. But we know what x sub A is. X sub A is known from this relationship here, and so we'll substitute that in for that, and then this gives us 1200 minus v sub A times t is equal to v sub B times t. And we know what v sub A and v sub B are. That was given to us. That's up here. Okay, so let's go ahead and solve for this. That means that we have, if I take this term to the right hand side, I'm going to have 1200 is equal to v sub A times t plus v sub B times t. That means that 1200 is equal to the sum, if I factor out a t, it's going to be the sum of those speeds times, I factored out the common t there, and this was the unknown, so let's go ahead and solve for that. So that means that t is equal to 1200 divided by v sub A plus v sub B. Okay, now let's go ahead and put in the known values of v sub A and v sub B. T is equal to 1200. Now I'm going to just go ahead and put units so that you can see that in fact dimensionally all of this is going to work out. V sub A is 200 kilometers per hour. V sub B is 100 kilometers per hour. That means that t, notice that the kilometers cancel from the top and bottom, and this hour is going to actually pop up on top over there. So we get 1200 divided by 300 hours. Notice also that I can cancel these two zeros with those two zeros, and so finally what I'm left with is 12 divided by 3, or t equals 4 hours. Okay, now that was the algebraic approach. Let's also go ahead and redo this problem in a graphical approach, okay? between the two, hopefully you'll get an appreciation of the physics and also see how to go about solving problems like this. So to do this in a graphical approach, let's go ahead and draw a displacement or a position versus time plot. I'm going to make this axis the time axis. This is in hours. And this will be the position axis in kilometers. Now, the problem statement told us that let's take the origin to be the starting station of train A. So that means that the position for train A is going to be at a 0 here of x. However, we know that the two trains are separated by 1,200 kilometers. So let's just say that the 1,200 is out here. Let's do the easiest one first. We know that for train A is moving at a velocity. So let me recall that VA is 200 kilometers per hour and that VB is 100 kilometers per hour, and that the distance between the two is 1,200 kilometers, which is that value right there. Now, the fact that train A is moving at 200 kilometers per hour, we already said that algebraically this would mean that x sub A is equal to 200 times the time. This is the distance is equal to rate times time, okay? So, well, this is just the graph of a straight line having a slope of 200. So it's going to have some kind of a slope. Let's suppose it's doing something like this, such that this is representing 200 kilometers, and this is for train A. Train B, on the other hand, has an equation of distance is equal to rate times time. In this case, however, we're going to say that this 100, which is train B's rate, times the time, we're going to note that it's going in the opposite direction, so it's going to have a negative slope. And so I'm going to note that this is also a straight line, but it's starting away at 1,200. And so because of all of this, this is like the y-intercept. That means that train B is starting at 1,200 kilometers away from where train A started. It's going in the opposite direction of train A, headed in opposite direction of train A, and so we'll say therefore we'll make it negative. Okay? Now, because it's negative and it's 100, we can note its graph to be something like this. This is train B. What we're really interested in is the intersection of these two. This is what we want to determine. And train A has a graph that looks like this. Train B has a graph that looks like this. And the intersection can be found by equating the two equations. Okay, let's go ahead and do that. So by equating the two, I'll take 200 times the time and equate it to the minus 100 times the time plus 1200. Okay, the 200 times the time came from train A's graph of the straight line, and the minus 100 times time plus the 1200 came from train B's graph of the straight line. And now it's just a matter of solving for the time. So if I bring the minus 100t to the left-hand side, that becomes a plus 100, plus 100 onto the 200t becomes a 300t, is equal to what we're left with on the right-hand side is the 1200. And so we see that the time is, once again, we can cancel out these two zeros on the left and the right just by dividing by 100. And so you're left with t is equal to 12 over 3, or t is 4 hours. And that's the time when the two trains are going to pass each other. It's going to take a total of 4 hours for that intersection to happen on those two parallel tracks. I hope that was helpful to you, and we'll look forward to seeing you in a future video.